Hi all, I'm Heather Beadle and I'm going to be showing you really quickly, hopefully, some work that David and I did looking at how we can use vector plots, LIME and SHAP for seismic facies machine learning evaluation. This is one of our current studies areas of research. The main whole idea around this is how much do we want to trust seismic facies models made from different machine learning techniques. So these are where we put in a whole bunch of different seismic attributes. They kind of go into whatever model you like, whether it's supervised or unsupervised. It gives us out a result. In this case, I'm going to show an example with random forest. And how do we know we can trust it? How do we know what decisions are going on in the algorithm? Are there ways that we can make the results a little bit more interpretable, more trustworthy for us as geoscientists as we move forward using these seismic facies models? And so today I'm going to quickly go over three methods we have in our AASPI consortium group that we use, from vector plots to LIME to SHAP. And then there's some other methods we're kind of more looking at in terms of early stage of research, which are partial dependence plots and accumulated local effects. So I want to quickly go over highlights of how these three techniques work. Vector plots is a simple query tool that we built into our AASPI software. It's in a lot of softwares. It's essentially a pixel by pixel analysis. So we can take our seismic facies classification and use the 6 attributes that we had put into it to be classified. and then we could click on each pixel and get the values of what each of the seismic attributes was. So very simple, very straightforward. But if we want to understand the seismic facies a little bit more quantitatively, what we really want to do is be able to kind of click on a pixel or understand, okay, why is this area marked by the yellow star? How's it making its decision? So is it classifying it differently depending on if the total energy attribute is more than 400 versus less, or what the dip deviation is? And so we really want a way to kind of query what's going on and then understand how those decisions are built into the prediction. So in this case, that pixel was 91% shale. And so LIME and SHAP are two methods that can help us with these insights. So LIME is local interpretable model agnostic explanations. This is a method that was first proposed in 2016. And what it does in a very basic sense is it focuses on explaining the individual predictions that are made by the AI model. So it tries to make it a little more simpler for us to understand what's going on in that local single prediction. And the way it works is you kind of pick the area where you want that prediction. So what part of your model do you want to understand why it classified the seismic facies that way? And then it creates a lot of variations, perturbs the input data around that specific data point, so pixel, voxel. And then it tries to explain visually what's going on. And so some of the things to keep in mind with LIME is, as I mentioned, it's local. So it's explaining one decision at a time, not the whole model. And it can work with a lot of different AI models. It's model agnostic. And so these explanations can be very intuitive for geologic interpreters. In this case, I'm kind of showing on the right-hand side at this purple star where we're in a channel. It's telling us that the peak magnitude there of our attribute is tending it towards not being a channel, while as those that are marked green, like GLCM homogeneity, coherent energy, peak frequency, the values it's seeing at that local point are tending it towards being in that class of a channel facies. SHAP is another method. It's been around since about 2017. It's Shapley Additive Explanations is what SHAP stands for. And what we like about this is it allows model interpretability, again, for many different models, and it gives you features importance. What's a little bit different with SHAP is that it can work on the local scale for a single prediction, and then also the global scale, so trying to explain your entire seismic facies model. Another reason we like this at AASPI is because it's very consistent. So the sum of all the different features or attribute contributions equal the difference between the actual prediction and the average prediction. So it's it, it's kind of summing things up in a way that is a little bit more reliable and a little bit more understandable, especially on the global scale. And so SHAP can give us information at the local scale. So we get these SHAP force plots, which in this case is shown at that same purple star I showed before. But then we also get a summary plot, which is globally over the entire model. So in this case, the summary plot is showing that high values of GLCM homogeneity over the whole random forest model are tending towards a channel classification, while low values of GLCM homogeneity are tending away from a channel facies classification. So let's look at this with some data really quickly. This is the data set I'll be using. It's the Waka 3D data set in the Canterbury Basin of kind of off the southern island of New Zealand. It's a lovely data set. And what we're going to be focusing on are channel complexes, turbidites, and background shales. So we're going to be classifying for 3 seismic facies in this area. Kind of the generalized methodology, it's pretty standard for any seismic facies classification, from preparing the data and calculating the seismic attributes, optimizing your machine learning model, from choosing which type of model to use to preparing the data sets, training it. And then we apply the explainable AI techniques. So in this case, we'll use 3 different techniques. And then we're going to analyze it and kind of use our geological expertise to integrate machine learning, the machine learning models with our geologic interpretations. In the AASPI software, we pick polygons as inputs for the random forest classification. So this is just an example of a few of them that I picked when training this random forest model. And then we can calculate a bunch of different attributes in AASPI or any other software, honestly. So 6 of the ones that I calculated were based on a project that Tao Zhao did back in 2015. So I already identifying good attributes for this area. So from coherent energy to curvedness, a couple of GLCM attributes, peak frequency, and peak magnitude. And so these are the inputs to the random forest model. And so if we look at the results, we've got some areas that are background, an area, that's a channel, a turbidite kind of marked in green. And one thing I'll focus on later is this kind of blue star, which is an area of interest for me. So perhaps it's a misclassification to look at. So with vector plots, this isn't a true explainable AI method, but it's a great investigative tool. We can click on that voxel of the turbidite and get an idea of what these attributes are. And so we can do the same thing with channels, with the background voxels, and that area of interest. And so one of the things we notice is there's a lot of similarity between channel and the background voxel in this particular case. And it's kind of similar to that area of interest, that potential misclassification. So that tells me that as an interpreter, if I want to understand and fine-tune this model, that I need to investigate further. And so overall, vector plots is a great qualitative tool for spot checking, but to do a full analysis on this, that would require significant effort on my part. So moving on to LIME, like I mentioned before, it reveals the relative importance of each attribute for each of the different seismic facies class. And it can give us insights into the machine learning's cutoff ranges for each class. And so in this case, we can look at the channel facies at that particular spot, see which of the attributes were tending towards each channel facies. So where that purple kind of star is, LIME tells us that there was a 91.6% kind of, not chance, but probability is the right word, that it's a channel, a 7.7% chance probability that it's a background. And then we could also look at the cutoffs that I'm showing on the right side of the screen. So to be a channel, to be classified as a channel, the coherent energy tended to be above 0.07. So we can do it quantitatively and qualitatively. We can look at that same spot with the SHAP force plots, which again are allowing local interpretability. So in this case, what the force plots do is they show us which direction each attribute is pushing us towards our classification. So with SHAP, it found a 92% probability that it would be a channel, so that was its prediction, starting with an average of 33% because 3 facies, so a 33% chance that it's any of the 3. And so GLCM entropy, peak magnitude, curvedness, they all pushed it towards being a channel, as did peak frequency, the coherent energy, and GLCM homogeneity. And so we could also look at the force plots for the other predictions, which were less likely, and understand how those attributes are playing in there. And one thing you'll notice here is that these kind of prediction probabilities were very similar between SHAP and LIME. So nothing drastically different or alarming between the methods. So I just want to pause and summarize these local pixel by pixel methods. From vector plots, which was a very simple query tool, showed us the values at each pixel point, to LIME, which can work with any machine learning method and gives us those local explanations of what's going on with each attribute, and then to SHAP, which again works for many machine learning methods. But one of the things here, like I mentioned before, is it's additive. And so you can kind of see a little bit more clearly how each of these attributes is building up to the final model. As I mentioned, SHAP also has summary plots, so on a global scale. So this is great, and this is where I could start to solve my misclassification issue. So we have our SHAP summary plot, which is showing us for the turbidites in blue, peak magnitude is the largest bar, and so peak magnitude was the most important attribute for identifying turbidites. Whereas for green, those channels, peak magnitude was a little bit less important. And so we can look at the sizes of these bars in the SHAP summary plot and understand which attributes were most important for which seismic facies. We can also look at it in these violin plots that I'm showing on the right-hand side. And so these show you how it breaks down with a little bit more nuance, which I've found very helpful in my analyses. So looking at turbidites, you can see on the top of the violin plots that a blue, so for peak magnitude, blue means a low value. So low values of peak magnitude made it less likely to be a turbidite, whereas higher values in the pink or reddish colors, you had higher values of peak magnitude for turbidites. And so you could spend a lot of time going through these. And there's other types of plots, like dependency plots, that you can get with SHAP that provide even more insight into what's going on. And so in this case, I just want to quickly show how I looked at this classification area. I noticed, that blue, it's being classified as a channel. To me, just with the 3 seismic facies that I identified, I would think maybe it's more of a background. And so one of the things I noticed is that coherent energy was a big player between these two. And so I could pull up my coherent energy attribute and look at it. And, what I noticed right away, and this is, kind of why we need interpreters to work with these machine learning models, is that this doesn't look like background. This doesn't look like a channel, but rather to me, it looks like a potential channel splay. So now I have to think about, okay, do I need to put in another seismic facies? Like, do I want to add a 4th seismic facies to my analyses? And so those are the types of inputs or insights we can get with different explainable AI methods. And so overall, like, we're finding that explainable AI has been a great tool for the AASPI research group, helping us kind of bridge machine learning and geology, taking a little bit of that black box aspect out of our analyses and allowing us to improve our models. So a tool for understanding, but also a tool for improving. And so thanks for listening to me for the last 15 minutes. If you're interested in trying out AASPI, We have a lot of built-in machine learning models, a lot of seismic attributes. That's kind of what we're known for. Or just learning more about our research group, feel free to shoot me an email at aaspi@ou.edu. If you want more information on SHAP, David Lubo wrote an amazing paper published in 2022 in Interpretations, really going into the details of SHAP, and you could find that on our webpage. We also have a lot more information about our attributes and machine learning research that we've been doing at the University of Oklahoma on our YouTube channel and on our LinkedIn page. So thanks again and have a wonderful day.